welcome to this talk. I'm going to present essentially the understanding of expression, a qualitative study of notional-machine-based exam question. Let's start by defining some of the terminology used in this title. What's a notional machine? A notional machine is what we call these pedagogical devices that are used to explain specific aspects of programming. They can be about something concrete or something more abstract. Here, as an example, we have the domino gates using, logic operation using domino gates, so something concrete. And here you have something more abstract, which is a memory diagram to show the memory during the execution of a program to understand how references work and how the program is executed. So why do we focus on expression? Well, expressions are the most prevalent construct in most programming languages, even those that are not predominantly functional. So let's take a look at this code snippet here. This is binary search implemented in Java. And if we were to highlight all the tokens that are expression, you can see that it would be most of them. In fact, it has been shown that in Java programs written by students, 53% of the tokens are expressions. So we have notional machines that are used to explain aspects of programming, and expression, which are the most prevalent constructs in programs written by students. And so we have a notional machine for expression. It's called expression S3. This notional machine is what you see on the right. It's a tree, and it's similar to an EST, which are the abstract syntax tree used in compilers and to specify the semantics of programming languages. And you have expressions written in code, and expressions are like Lego blocks. You can assemble them. So you have some expressions which are represented by nodes, and you compose them. So here you have the msg.length equal expected expression, and this is the representation in the expression S3 notional machine. So you can use expression trees to understand the structure of expressions, but you can also use them to type check the expressions. So we can annotate the individual nodes using types like a type checker would do. So we have here MSG, which is a variable of type string according to the code snippet here. Then we have method length, which is a method of the class string in Java, has type int. Then you have expected, which is another variable of type int declared there. And then you have equal index expression, which is a Boolean to compare two values. So we can annotate the nodes with types, but also with values. So let's say that we have the method checkLength invoked with the arguments hello and 4. We can use the expression S3 notional machine to evaluate the expressions like they would be evaluated when you run the program. So you start at the bottom and you do evaluate MSG, which is hello, length, which is 4. And then to evaluate the top node, you need to also evaluate the right-hand side. So you need to evaluate expected, which has value 4. And then you compare 4 and 4, and you get true. You can use this notional machine both in free-form context, which means that you can use it on a paper or on a whiteboard, or you can use it in a more structured editing environment, such as our platform, Expression Tutor. Now, we use expression trees in exam question as well, which means that we use it for assessment. This is an example of an exam question that was asked to students. They were given a code snippet. You can see that the top the 2 method definitions in Java, and they had 3 tasks. The first task is to draw an expression tree for the expression in the return statement of the compare method. So this first task asks to do 2 things. First, the student needs to understand which tokens inside the code snippet are expressions, and then they need to draw the structure of the expression. I'm going to show you here the solution while I talk. And then the second task is to annotate each node with a type. So we have drawn the structure for the first task, then we need to add the nodes, the labels of the types to each node here in blue. And then lastly, assuming that the method is invoked with certain values, we need to annotate all the nodes that are evaluated with the correct value. That would be the labels in green there. Now, we've been using this in multiple exams across multiple years. And so we decided to study these expression trees. And so what we wanted to find are these three things. What are the most common mistakes students make using this notional machine? What are the likely causes of these mistakes? And what relationships do these mistakes have to programming languages misconception? We have a corpus of 542 hand-drawn expression trees collected from 12 different exams of university courses at 2 different educational levels, in which this notional machine were used throughout the course. So the students were already familiar with it. The exams were across 4 different years, and the expression trees of all the exams in total involved 12 different expression constructs, meaning 12 different concrete language constructs from the actual Java specifications. So how do we do our qualitative analysis? First, we need to systematically capture the deviation from the correct solution. The important thing to note here is that each tree has one and only one correct solution, because the solution is given from the formal specification of the language, in this case Java. So it's not possible to have 2 correct solutions. There's only one, so we can systematically capture the deviation from it. Then we need to connect these differences to the actual programming languages concepts. Then we need to take these concrete deviations and assign some form of higher level logical mistakes to them. And finally, we connect languages misconception. For this presentation, we're going to focus only on the first 3 points of this analysis. So let's see how we coded our deviations. So we have this example of a expression here as .length method invocation on the length method on a string in Java. And this is the student snippet, which means this is a subtree of an expression tree drawn by a student in an exam. And this is the reference solution. So you see that according to the Java specifications, an instance method invocation has as the target a sub-expression, which means that the S here, which is a variable, should not be inlined into the method invocation node. So how do we record this deviation? Well, we say that it's a deviation about the structure of the expression tree. It involves a simple variable access, which is the name of this construct, the S variable. And what happened to it? It was inlined into a method invocation. And we classify this as a higher level logical mistake called variable inline. Now, a variable may be inline in method invocation, but they may be also inline in something that is not a method invocation. And vice versa, a method invocation may have something inline in the target call something that is not a variable. And so we need to also collect the deviation about this mistake from the other side. So we need to say that there is a deviation in the structure, this time for a method invocation node, which has an inline child, which is its target. And the logical mistake is target inline. So this is the structure of our codes. We have 5 parts: aspect, construct, operation, qualification, and logical mistake. The first part in gray there, the physical difference, is composed of the aspect, which is either structure, types, or values, which corresponds to the 3 aspects of the programming languages that we are looking at using the notional machine. Then we have the constructs, which are the actual Java constructs that are involved in the deviation. The operation, so what happened to that particular construct. And for the operations, we used pre-editing distance algorithms operation, and plus some more, because since these expression trees are drawn on paper, they are free, so there's no guarantee in the first moment that those trees are actually trees, that they can be anything because there's no constraint on their form being on paper. Then there is qualification, which is not very meaningful, but it helps characterize the operation. And finally, we have the logical mistake, which is higher level. To look at the first four, you only need to compare the student snippet to the reference solution, while to define the logical mistake, you also need to reason about the language. So as I anticipated before, a mistake can occur across different constructs. So going back to the example I've shown before, we had the variable which was inline into a method invocation, but the same mistake can happen also, for example, here in an array access or here in an infix expression. The results that we obtained were that we recorded 2,046 deviations using 3 different aspects, which as I'm showing before, 12 constructs, 15 operations, and 51 different logical mistakes. An interesting thing about these 51 different logical mistakes is that the top 10 mistakes with respect to prevalence were featured at least 20% of the times in the exams of the students, meaning that when a mistake had the opportunity to occur, we found it at least 20% of the times in the top 10 mistakes. So now I'm going to show you 5 mistakes selected among the top 15. The criteria for them was that they should have been diverse enough between them because some mistakes are similar to others, and that we should cover all 3 aspects that we are looking at using our notional machine. And also the student snippets I'm going to show here are actual student snippets from actual exams, but they were withdrawn for privacy purposes. So let's start with the first mistake here, logical mistake here. So we have this expression, which is a equal null question mark x id ai to string. So basically what we are doing here is that we have a conditional expression that is guarding an array access to prevent a null pointer exception, right? So if it's null, we return a string literal, otherwise we can perform our array access without risking to incur into a null pointer exception. So this is the student snippet, and the structure is correct. But if we compare this to the reference solution and we look at the values that were annotated on top of the nodes by the students, we can notice that there is a difference. So here, the node X is annotated, while it's not annotated in the reference solution. Why is that? Well, in a conditional expression, you are not going to always evaluate all sub-expression, right? That's the purpose of the conditional expression in the first place. If A is null, we are only going to evaluate the first branch, this one. If A is not null, we're only going to evaluate the right branch here. And so if a student shows that they are annotating both branches, it indicates that they don't understand that how conditional expression works. And if this were to be evaluated in a situation in which A was null and the students try to annotate also this branch here, they will get a null pointer exception here because you cannot access an element of a null array. And this is made even worse if we take into consideration the fact that in Java you could have side effects as well. So this mistake is called both branches of conditional expression evaluated. It was featured 58.3% of the time in the students' submissions. And it's number 1 with respect to prevalence. Next mistake, here we have this other expression. We don't really need to focus on it right now. We need to look at the student snippet. What we see here, if we compare to the reference solution, is that the literal nodes are not annotated with value. Why is that? That is because there is a well-known programming languages misconception in which students believe that literal are not expressions, and so they don't have a type, and sometimes they don't even need to be type checked. In fact, there exists a similar mistake that's not about values, but types for literals. So this mistake is called literal without values. And there is also one literal without types because of this well-known misconception. Next, we have this is still again the same expression. It's a string concatenation, right? And here the students wrote this, which is basically they took all the binary operations of the classes and flattened them into a single node. So this would be the reference solution. The expression is left to right. So you have AI and then the conditional expression here. Then you have the plus and then the 0 here. And here instead they flatten everything. This shows that the students does not understand that even without parentheses, binary expressions are still binary expressions. So you need to nest them properly. This could be attributed to the fact that, for example, here we have a sequence of pluses, and pluses are at the associative and commutative in algebra. So the students say it doesn't really matter which order I'm doing them. But in a programming language like Java, you also have side effects, which then make this property no longer hold true for classes, because you could have a side effect in the middle, and then the order of evaluation would change the actual program execution. The name is operator sequence flatten, and was featured 37.5% of the times. Next, here we have this other expression. We need to focus on the GT method invocation, and that is its definition. So the students wrote this instead of invoking the method invocation, writing the method invocation node, which is the expression found within the return statement of that method invocation. And this is called substitution taken from evaluation. It's a mistake that occurs in many forms where the students take one node and substitute it with a subtree that contains an expression from the evaluation part of that original node. So here, for example, we have GT, and it's replaced with A greater than B there in the return statement. And it can also be even more than one step of evaluation. Students sometimes go out of their way and build entire subtrees that end up being way more complicated than the original expression. And so this shows that the students have difficulties in understanding the dualism between the static part of the code, which is the code that's written there, the expression, and whatever is evaluated. So they would perform a substitution of the method invocation here as an example. Finally, we have this one. So we have to look at the code snippet there. We have an interface and then two record classes, empty and const. So this is a simple linked list implementation of strings. So here you have const A, new empty. And then this is what the students did. So they annotated the node empty with type sec, which would be the type that you see in the constructor of const, instead of writing empty, which is the actual correct type, this node. Why is that? Is because the students did not understand correctly how expressions are typed, so they didn't reason about this expression in isolation, but they looked at it from the point of view of the constructor, and so they set the type as the parameter whole type, which will be the type of this constructor here. So to summarize, these are our top 10 occurring mistakes. Most of them we have seen here, the examples of them, and the variety of mistakes that were found using these notional machine-based exam questions can show us multiple insights into how students understand several different aspects of programming. Thanks.